We will see how to solve problems of balancing of rotating masses on same plane and also on different planes. So initially we will see balancing of rotating masses on same plane. So in this case, I have considered three rotating masses here. First mass is A, second one is B, third one is C. The mass on the first one is MA, second one MB, third one MC. First mass is making an angle theta A with reference. Second mass is making an angle theta B with reference. Third mass is making an angle theta C with reference. So, because there is some unbalance in the system, I have added one balancing mass which is denoted by dotted line here. This mass is called as balancing mass. This balancing mass is making an angle theta d with the reference. So originally there are three masses in the system A, B and C. In order to make the system to balance, I have added additional balancing mass which is D here. So I should find out the parameters of this balancing mass. That means the angle made by the balancing mass or mass of this balancing mass or radii of rotation. So to find out these unknown parameters, I am going to form a table here. So in this table, if you observe here, the header for the table header titles mass, radius, angle. Okay. So mass MA, MB, MC. These three are the masses in the original system. The corresponding radii of rotation are RA, RB and RC. The corresponding angular positions are theta A, theta B and theta C. Because I have added one balancing mass here, so I am going to add fourth row which is representing the balancing mass. Mass MD, radius of rotation RD and angular position theta D. So these parameters represents the balancing mass which I have added additionally. Okay. So because once I add this balancing mass, the entire system is in balanced condition. So I am going to determine the horizontal component of force and net horizontal vertical component. So horizontal component of centrifugal force. So M R cos theta. M R multiplied by cos theta. We have to fill that value. Vertical component is M R sin theta. So for each mass, we have to find out the horizontal components of all the forces and vertical components. As the system is balanced, the net horizontal force should be equal to 0. The net vertical force should be equal to 0. Solve these two equations and get the unknown parameters. Okay. So in this case, we have seen there are three masses in the system and I have added an additional balancing mass to make the system balance. So the total there are four masses after addition of balancing mass. Okay. Now I'm going to take another case here. Okay. Now we will see one problem here. Okay. So there are four masses. There are four masses here. The masses are 400 kg, 300 kg, 240 kg, 260 kg. The corresponding radii of rotation are also given in the problem. Angle between successive masses are given. That means angle between 1 and 2 is 45, angle between 2 and 3 is 75, angle between 3 and 4 is 135. You are asked to determine the balancing mass parameters. The radius of rotation for the balancing mass is given to us. Because the distances between the planes are not given, this is a problem of same plane. So if I draw the angular positions, so I have first mass, I have taken first mass as the horizontal mass, horizontal line. That means theta equal to 0 for the first mass and this is taken as reference. Then second mass is at 45 degrees, 1 and 2 angle is 45. Between 2 and 3 it is given as 75. Between 3 and 4 it is given as 135. I have added an additional balancing mass. I don't know the value of theta for that additional balancing mass. Okay. Now when I fill the table, first we will see the angular positions. I am going to take this mass as the reference here. So all the angles should be measured from this reference. So for theta 1 it is 0 because I have taken 1 as the reference. Theta 2, angle of mass 2 from 1, 45. Theta 3, angle of mass 3 from 1, from 1. So total 75 plus 45. Theta 4, angle of mass 4 from 1. That means 135 plus 75 plus 45. Theta B, I have assumed that from 1 itself. So directly I can write theta B. So when I fill the table, all the masses, the radii of rotation, observe the angles here. So angles for 1, because I have taken it as reference, it is 0, and all the remaining angles. Then horizontal component m 200 or 0.2 cos 0, you will get the value as 40. So mr cos theta. Similarly mr sin theta for the first mass, 200 into 0.2 into sin 0. See, like that you can calculate all the parameters, all the horizontal components and vertical components. Now you have to take this horizontal component net equal to 0. The sum of all these components should be equal to 0. The sum of all these vertical components should be equal to 0. So first one is sum of all the horizontal components equal to 0. You will get one equation. Sum of all the vertical components equal to 0. You will get second equation. Okay. Now you have to solve these two equations. The easiest way is take the ratio of 1 and 2. So if I take 2 divided by 1, here 2, this equation divided by this equation. So on this side 0.2 gets cancelled out, mb gets cancelled out, sin theta by cos theta you will get tan theta. Okay. So I have taken the ratio of 2 and 1. I got the value of theta b. I got the value of theta b. Then when I square and add both the equations, I will get mass b here. I will get mass b here. Okay. So when balancing of rotating masses problem is given on a single plane, okay, so first you have to fill the table m r theta, mr cos theta, mr sin theta. These are the columns. Now if I take the second case where rotating masses on different planes, so here I have taken 4 rotating masses, 1, 2, 3 and 4. One is on a plane, 2 is on another different plane, 3 is on another different plane, 4 is on another different plane. So all these 4 masses are on different planes. So when in the problem, when you are given the distance between the planes, then it is the rotating masses problem on different planes. Okay. Now in the earlier case, when the masses are on same plane, we have added single balancing mass. But here, when masses are on different planes, we have to add two balancing masses. So first balancing mass mb1, second balancing mass mb2. So originally there are 4 masses in the system. I am adding 2 balancing masses. So total there are 6 masses in the system here. So first balancing mass is on one plane, second balancing mass is on another plane here. So there are 6 planes. Originally there are 4 planes, 4 rotating masses. When I add 2 balancing masses, the number of planes and the number of masses becomes 6 here. So whenever the masses are on different planes, we have to add 2 balancing masses on 2 different planes. Because the masses are on different planes, couples come into picture here. Okay. So if we observe the table here, m, that is mass, r, theta, all these three are same. I'm going to add additional column which is distance, which is used for couple. So force components are same, mr cos theta, mr sin theta. Couple components are mr cos theta into L, mr sin theta into L. So we are going to add 3 additional columns here. One is the distance column, another one is couple horizontal component, and another one is couple vertical component. Okay. The remaining procedure is same. The net horizontal force is 0, the net vertical force is 0, the net couple horizontal is 0, net couple vertical is 0. Solve these 4 equations, you will get the unknown parameters. So whenever the masses are on different planes, and if it is necessary to add balancing masses, we have to add 2 balancing masses on 2 different planes, and the couple comes into picture here. MRL cos theta and MRL sin theta comes into picture here. In the same case, there is one more type of problem. I have 4 rotating masses here. but without adding balancing masses, the system should be balanced. What does that mean? I don't know m1, I don't know m2. So what should be the values of m1 and m2 so that the entire system is balanced without addition of balancing masses? Okay, so here there are four masses in the system. Okay, I don't know some parameters related to these rotating masses. Okay, so I am not adding any balancing masses here, but because of these four masses, whatever forces and couples are generated, they should be balanced. That means the net should be 0 here. So in the earlier case, by addition of balancing masses, we have made the system as balanced. In this case, without addition of balancing masses, by changing the parameters of rotating masses in the system itself, we are balancing here. Okay. So there are four masses in the system and four masses, forces and couples because of four masses should be balanced here. The remaining procedure is same. Now we will see a problem related to this. So there are four masses which are completely balanced. Four masses are completely balanced. What does that mean? I am not adding any additional masses here. I am not adding any additional masses here. Okay. So masses C and D make 90 and 195 with respect to B. Because the angles are given with respect to B, I have to take mass B as reference for angles. So mass B I am going to draw as horizontal and I am taking that as reference for angles. Magnitudes of masses of BC and D are given. Radii of rotation are given. Distance between B and C only is given to you. So distance between B and C is given means the masses are on different planes. The masses are on different planes. So if you observe the diagram here, okay, so the masses are on different planes. So there are four planes, four masses. I am not adding any additional balancing masses because the system is balanced because of these four rotation of these four masses only. The angle between B and C is given 90 degrees. The angle between B and D is given as 195 degrees. So I have taken B as the reference. I have taken B as the reference here. Distance between B and C is given. Distance between B and C is given. Other distances I don't know. So I am assuming this as LB and I am assuming this as LD. So I have taken this A as reference for distance. So A is reference for distance, B is reference for angles. Now when you fill the table here, okay, all the masses are given to you. Four masses. Radii of rotation is given to you. Okay. Whatever angles we know, mark those angles here. Here B is 0 means theta B is 0. Distance is A is reference means distance for A is 0. Find MR cos theta all the components, MR sin theta all the components, MRL cos theta, MRL sin theta. Then equate the net resultant to 0. So net horizontal force 0. That means sum of all these four components equal to 0. You will get one equation. Sum of all these components is equal to 0. Second equation. So solve these two equations. You will get MA and theta A. Then take sum of all vertical components equal to 0. You will get another equation. Sum of all coupled components equal to 0. You will get two equations. Solve them. You will get unknowns. So whatever may be the problem, whether they are balancing masses on different planes or balancing masses on same plane, okay, you can find out the unknown balancing masses. If the masses are on same plane, then only one balancing mass. Masses are on different planes, two balancing masses. Okay, if the system is balanced because of rotation of the masses themselves, there is no need to add any balancing mass. On same plane, you have only force vertical and horizontal. MR cos theta, MR sin theta. On different planes, MRL cos theta and MRL sin theta. So using this concept, you can solve the problems.